Hello dear students, welcome back to the lecture series on the course MTH 802 Topology Second. In this lecture we are going to discuss Tietz extension theorem. So first of all, in previous lecture we have seen the Eurygen's lemma that we have done in previous lecture. So in the first I would like to write the general form of Eurygen's lemma. General form of Eurygen's lemma. Eurygen's lemma. Okay. General form of Eurygen's lemma. Okay. So which is let X be a normal space. Let X be a normal space, and let A and B be disjoint closed subspace of X. Be disjoint closed subspace of X. Be disjoint closed subspaces of X. Closed subspaces of X. Now if AB area is any closed interval, is any closed interval, then there exists a continuous function. There exists a continuous function. Then there exists a continuous function f from X to the closed interval AB, such that it maps each point of A onto A and each point of B onto B. That's the general form of Eurygen's lemma. That's the general form of Eurygen's lemma. So in previous lecture we have proved that given a normal space X and two disjoint closed subspaces of X, then we can find a continuous function f from X to the interval 0, 1, such that f maps each point of A onto 0 and each point of B onto 1. But here we have a general form of the Eurygen's lemma, that if we have any closed interval AB, then we can find a continuous function f from X to the interval AB, such that it maps each point of A onto A and each point of B onto B. So by Eurygen's lemma, by that we have already done, by Eurygen's lemma, there exists a continuous function. Okay, there exists a continuous function g from X to the interval 0, 1, such that G maps each point of A onto 0 and each point of B onto 1. So this is already done. Now I will construct a new function from X to the interval 0, 1, which is also a continuous and which maps each point of A onto A and each point of B onto 1. So let's define that map. Define f from X to the interval A, B by, let's define this map by f of X is equal to B minus A times G of X plus A. Since G is continuous, therefore f is continuous, and you can easily verify that it maps each point of A onto A and each point of B onto B. Since G maps each point of A onto 0, so therefore what will be f of A now? F of A is equal to B minus A G of A, but G of A is 0, so that means f of A is equal to A. And what's f of b? F of b is equal to b minus a g of b. And what's g of b? G of b is 1. So it means it's f of b is equal to b minus a times 1. That's equal to b minus a plus a, which is equal to b. And it's also a continuous map. And since this range of g is 0, 1, therefore range of f, you can easily verify it's the closed interval a, b. So that's the general form of Urizin's lemma. So then you can see, then g is continuous, then f is continuous, sorry. F is continuous, then f is continuous such that it maps each point of a onto a and each point of b onto b. So this can be easily verified. It's very simple. So now we state our main theorem, that is T is extension theorem. First we'll write down its statement, then we'll prove it. Okay, so let's state this T is extension theorem. T is extension theorem. Okay. So statement of T is extension theorem statement. Let X be a normal space. Let X be a normal space. F a closed subspace of X. F a closed subspace of X, and this f is a continuous function from f to the interval a b. Then we need to show that this f can be extended to the whole space, and it can be extended continuously. So then f has an extension. Then f has an extension. F has an extension f dash from X to the interval a b, such that f is an f such that this f dash is also continuous. Is continuous. This is continuous. Extension f dash, and this map f dash. Extension means that when we restrict this f dash to that closed subspace, it's same as f. So f dash restricted to f is equal to f. So that means restriction. F dash restricted to f is equal to f. That's the restriction. So it's very important theorem, because this f is a continuous function from the closed subspace f of X to the closed interval a b, and that f can be continuously extended to the whole space. That's the importance of this theorem. So let's prove this theorem. In case a is equal to b, then there is nothing to prove, because since f is a continuous from f to the closed interval a b and a is equal to b, so therefore f must be a constant function. It's equal to a throughout. And we can obviously extend this f to f dash to whole space by taking f dash equal to f dash of x equal to a for each x in X. So that's in that case it is simple. If a is equal to b, then there is nothing to prove. So assume a is less than b. And as in case of Urizin's lemma, we can assume that a is equal to -1, b is equal to 1, because in case of Urizin's lemma, the particular form of Urizin's lemma, in that case we have chosen a is equal to 0, b is equal to 1, and here we can choose we choose a is equal to -1, b is equal to -1, b is equal to 1. Then we can prove its general form also for any closed interval a b. So as in case of Urizin's lemma, in case of Urizin's lemma, we can assume that a is equal to -1 and b is equal to 1. We can assume this. A is equal to minus 1, B is equal to 1. Now, actually, we in the proof of this theorem, we are constructing a sequence of continuous functions, and we start that construction with f, which is the given function f. Okay, so since this f is a function from f to closed interval ab, we started our construction. We take f naught is equal to f, then we define f1, then f2, and so on and so on and so on. Okay, so we begin by defining f naught is equal to f. So then, what is this f naught? It's a function from closed subspace of x, which is f, to interval -1 to 1. So it is its domain is f, because f naught is same as f. And domain of f is f. F is a function from f to closed interval ab, and here we have chosen this a is equal to -1 and b is equal to 1. So next we define two subsets of x. So let's define a naught, which is equal to, it's a subset of x. It's a subset of x. It's a subset of f. Sorry, it's a subset of f such that the values of f naught are less or equal to -1/3, and b naught, it's the set of the points in f. It's a subset of f such that f naught of x is here it's less or equal to -1/3, and here it's greater or equal to 1/3. Okay. Then you can easily verify that they are closed subsets of f, actually, because f naught is a continuous, so they must be closed, and because it is the inverse image of the closed subset of R. This a naught is the inverse image of -1/3 to infinity, which is closed subset of R, and that b naught, it is the inverse image of -infinity to 1/3 closed, greater or equal to 1/3 here. So both a naught and b naught, they are the inverse image of closed subsets of R, and f naught is continuous, therefore a naught and b naught are closed subsets of f. Page number 3. Now, since f naught is continuous, therefore a naught and b naught are closed subsets of x. Subsets of y, f, and f is itself a closed subset of x, and f is a closed subset of x. So therefore a naught and b naught are closed subsets of x. So also they are disjoint because a naught is a set such that the values are less or equal to 1/3, and b naught is a set such that the values of f naught are greater or equal to 1/3. So therefore they are disjoint, because there is no common point in this a naught and b naught. Suppose there is a point which belongs to both the sets, say x, then f naught of x must be less or equal to 1/3 as well as greater or equal to 1/3, which is not the case, which is not possible. So that means they are disjoint. So also a naught and b naught are disjoint. So they are disjoint. So because of this reason, they are disjoint. There is nothing common in a naught and b naught. Okay. Now we can apply Eurydice lemma. They are disjoint subsets of normals, or disjoint subsets of disjoint and closed subspace of normal space X. normal space X. Now we can apply Eury's lemma here. If A and B are disjoint closed subspace of a normal space X and we have any closed interval AB, then we can find a continuous function on X, f from X to interval AB, such that it maps each point of A onto A and each point of B onto B. So again, since here A0 and B0 they are closed and disjoint subsets of X, so therefore we can find a continuous function f from X to any closed interval AB. So let's choose the closed interval AB here, -1/3 to choose A equal to -1/3, B equal to 1/3 in that case. So by Eury's lemma, by a general form of Eury's lemma, you can say, by Eury's lemma, there exists a continuous function. There exists a continuous function. There is a continuous function G0, which is from X to the closed interval -1/3 to +1/3. So that's why Eury's lemma, such that it maps each point of A0 such that G0 of A0 is equal to G0 of A0 is equal to -1/3 and G0 of B0 is equal to 1/3. G0 of B. So now next we define the function f1. f0 is already defined. Now we define f1, which is equal to f0 minus G0. It's obviously a function from f to interval -1 to 1, because f0 is a function. The domain of f0 is f. Domain of G0 is whole space, but domain of f0 is not whole space. Therefore, the domain of f0 minus G0 cannot be whole space. And here this G0, this is the restriction of that G0 on the space f. So it's a function from f to interval -1 to +1. Then this function is a continuous. Then f1 is continuous. Then f1 is continuous. And you can one can easily verify that now we verify that this mod of f1x is less or equal to 2/3. So it's very simple. We take different cases on this x. In first case we take x as in A0. In second case we take x as in B0, and in the third case we take x outside of A0 and B0. So these three cases we discuss. If x is in A0, okay. If x is in A0, then G0 of x is equal to -1/3, because G0 maps each point of A0 onto 1/3. That's here. You can see it here. G0 maps each point of A0 onto -1/3. So if x is in A0, then G0 of x is equal to -1/3. And what's f0 of x? f0 is f0 of x. What's f0 of x here? f0 of x. So that's again the definition of A0 actually. f0 of x. What's the definition of A0? X in A0, so that f0 of x is less or equal to -1/3. It's less or equal to -1/3. It's less or equal to -1/3. So therefore, f1 of x, it's equal to, by definition, it's f0 of x minus G0 of x, and f0 of x is less equal to -1/3, and that one is less or equal to -1/3. So it is here plus. So G0 of x is -1/3, and f0 of x is less or equal to -1/3, and then minus times G0 of x. G0 of x is equal to -1/3. That's equal to 0, and 0 is less or equal to 2/3. So f1 of x is less or equal to 2/3. And on the other hand, you can see that so also you can see that this f0 of x, it's greater or equal to -1. because f0 is a function from x to the interval -1 to +1. So as this f0 is a function from x to -1 to +1. So that means f0 of x is always greater or equal to -1. So therefore f1 of x, which is equal to f0 of x minus g0 of x. So what's f0 of x? It's greater or equal to -1, and then minus g0 of x. What's g0 of x? It's equal to -1/3. So that means it's -1 plus 1/3, which is equal to -3 plus 1. That's -2/3. So therefore we have -2/3 less or equal to f1x. -2/3 is less or equal to f1x, and f1x here, it's less or equal to 2/3. So that means mod of f1x is less or equal to 2/3. So if x is in a0, then mod of f1x is less or equal to 2/3. And on similar lines, you can prove the other cases also. On similar lines, mod of f1x is less or equal to 2/3 if x is in b0. And the last case, if x is not in a0 and not in b0, so this can also be easily done if x is neither in a0 nor in b0. So that's again simple. That's not too difficult. So if x is not in a0, union b0. If it's not in this union, so then this is an exercise for you. Then show that mod of f1x is less or equal to 2/3. So that's an exercise for you, or you can see the proof of this from my notes, or you can do it yourself. So therefore mod of f1x is always less or equal to 2/3 for all x in f. So this is proved. So it's always less or equal to 2/3. So next we define a1. Now we define a1, another set a1, which is a subset of f, such that the values f1 of x is less or equal to -1/3 into 2/3. So that 2/3 is actually important here. And b1 is equal to x belongs to x, such that f1 of x is greater or equal to -1/3 into 2/3. So as in the earlier case, as in the case of a0 and b0, we have seen that a0 and b0, they are disjoint closed subsets of x. Similarly, they are also disjoint closed subsets of x. Then a1 and b1 are disjoint closed subsets of x. And x is a normal space, so therefore we can apply again Eury's lemma.